Welcome to Demystifying Math. In this lesson we're going to be discussing cycloids. This is part 2 in a video series on cycloids. The general parametric equations for a cycloid we found in the first video, which are x equals a times theta minus sine theta and y equals a times 1 minus cosine theta. If a is equal to 1, then the parametric equations are theta minus sine theta for x and 1 minus cosine theta for y. Let's see how the cycloid is drawn. Alright, so here we have a circle of radius 1 with the center of the ordered pair 0, 1. What we're going to do is move the circle along the x-axis and at the same time move point P around the circle. Point P is tracing out is following the path of the circumference of the circle. So when we have reached halfway around the circle, point P has traveled pi units. When point P has traveled completely around the circle, it would have gone of the distance equal to 1 circumference of the circle. Since our radius length is 1, that distance will be 2 pi. Now, at the same time, the circle is traveling that same distance along the x-axis here. What you should notice is that when point P reaches the top of the circle, it's reaching its maximum point on the cycloid as it traces out that cycloid. Where point P comes back down to the x-axis, we have a 0 of the graph. We also have a sharp turn there because it's going to turn around and come back up around the circle again. So you should also note that this is going to keep repeating over and over again as point P keeps cycling around the circle. Okay, so when we have a length of a equals 1, that's actually the radius of the circle that's used to trace out the cycloid. And the graph is periodic. It's repeating in this case every 2 pi units. It has sharp turns at all multiples of 2 pi, so we can call it 2 pi n, where n represents any integer. And it has relative maximum points halfway in between the sharp turns, in this case at pi, 3 pi, 5 pi, and so on. Or we'll call it 2n plus 1 pi. Now we discussed the zeros of the graph, and that's where point P is coming back around and completely going around the circle one time. So if it goes around the circle twice, it'll come back down and have another 0 on our graph. So we have, in this case, zeros at 0, 2 pi, 4 pi, and so on, are multiples of the circumference, which is 2 pi in this case. Alright, so we want to find the turning points on the graph, and we can do this just like we do with any other equation. We're going to look where our tangent line has a slope of 0 or where it has an undefined slope. So let's go ahead and look at our tangent line on our graph, and we'll trace it out. Okay, so here we have a tangent line attached to our cycloid, and what we're going to do is move our tangent line along the cycloid so you can look at the slope of the tangent line. Now notice that between 0 and pi your tangent line has a positive slope. Your graph is increasing between 0 and pi. When we come in on pi, you can see that your slope it comes close to 0 and your tangent line flattens out. And that's going to give us a maximum point. Now beyond that, in between pi and 2 pi, it's turning so that it's coming downward, so we have a negative slope on our tangent line. Our graph is decreasing on the interval from pi to 2 pi. Then we're going to reach this point at 2 pi, and what you should notice about your tangent line is it now has, it's a vertical line, and its slope is going to be undefined. It's actually going to end up being an indeterminate form, 0 over 0, for this particular graph, and we're going to look at that in a minute. Now, due to the cyclical nature of the graph, it's going to keep repeating those tangent line slopes. So between 2 pi and 3 pi, it's going to be increasing, so it's going to have a positive slope. And then when we get back to 3 pi, our tangent line is flat again, so we have another 0 slope. Okay, so we saw that we can find our maximum points where the slope of the tangent line is 0. For the sharp turns, our tangent line is vertical, and it's going to be an indeterminate form of 0 over 0. And in between our sharp turns, we have a nice smooth continuous curve, so we won't have any gaps in there. All right, we can find the slope of the tangent line by finding dy dx, but because we're working with parametric equations, we're going to find the derivative of y in terms of theta and the derivative of x in terms of theta. And then we're going to set each one of those derivatives equal to 0 to look for our critical points. So for our y value, we have 1 minus cosine theta, and the derivative of that is sine theta. We're going to set sine theta equal to 0, and that's going to give us theta values of 0, pi, 2 pi, 3 pi, 4 pi, and so on. Now we're also going to find dx d theta and set that equal to 0. So our x parametric equation was theta minus sine theta, and the derivative of that is 1 minus cosine theta, and then we're just going to set that equal to 0 and isolate cosine of theta. So cosine of theta is 1. And that's going to happen when theta is equal to 0, 2 pi, 4 pi, and so on. Now what you should notice is that our dy d theta and our dx d theta have some common critical points in common. So those are at 0, 2 pi, 4 pi, and so on. That's actually where the numerator is 0 and the denominator is 0, so that would be the indeterminate form. So when we want to look at the slope of the tangent line to be 0, we don't want the denominator to be 0. We want only the numerator to be 0. So those would be the values of pi, 3 pi, 5 pi, and so on. Then when it's indeterminate is when both the numerator and denominator are 0, so that's at 0, 2 pi, 4 pi, and so on. Okay, now with all our other graphs, we want to test for a sign change between our critical points. So let's try doing that with our dy dx that we found. So if we plugged in around pi, we're going to plug in below pi and above pi. So at pi over 2 we get out a 1, and at 3 pi over 2 we get out negative 1. So in between 0 and pi we have an increasing slope, positive slope of 1. And on the other side we tested out and got a slope of negative 1, so that means it's decreasing on the interval from pi to 2 pi. So that means that we have a maximum point at pi, and if we plug it back into our original equation we get out a 2. Remember that our circle had a radius of 1, so the diameter of 2, so the highest point that it's going to reach on our graph is at 2. Now we had also another critical point at 2 pi, so we've already tested to the left of 2 pi at 3 pi over 2, and we got a negative, so it's decreasing there. So we're just going to test above 2 at 5 pi over 2 or 2.5 pi, and I got out a positive, so that means it is changing from decreasing to increasing, which means that we're going to have a minimum point at 2 pi or at 2 pi 0 by plugging 2 pi back into our original function. And that happened to be the sharp turns for this graph. Okay, so using the cyclical nature of the graph, we can conclude that the relative maximum points occur where 0 equals pi, 3 pi, 5 pi, or 2n plus 1 pi. The minimum points are going to occur at 0, 2 pi, 4 pi, all the way up to 2n pi. Okay, now let's look at an equation that's a little bit different. In this case, we have an a value of 3, which means that the radius of the circle that we use to trace out the cycloid is 3. So let's look at the... Okay, so here we have a circle of radius 3. That means that the highest point on the circle is at the ordered pair 0, 6, and the lowest point on the circle is at 0, 0. And what we're going to do is the same that we did before. We're going to move the circle along the x-axis, and at the same time we're moving point P around the circumference of the circle. In this case, because my radius length is 3, the circumference of the circle is 6 pi. So when P has moved 6 pi units around the circle, it has completely gone around the circle once. So it's going back down to the x-axis, making a sharp turn, coming back up, and then going around the circle again. So it's going to cycle back around. So in this case, we have zeros at 6 pi and 12 pi, which are our turning points or our sharp turns. And then at 3 pi and 9 pi, I have maximum points where it's reached the top of the circle there. Okay, so what we want to do is use calculus to find our maximum minimum points. So our x equation is 3 theta minus 3 sine theta, and our y equation is 3 minus 3 cosine theta. I'm going to take the derivative of the x equation and the derivative of the y equation. And then what we want to do is divide them. So we're doing dy dx. So it's dy d theta divided by dx d theta. And we get sine theta over 1 minus cosine theta. So what you should notice is that we got the exact same derivative that we had before. So our critical points are going to be at the same values of theta. But remember that your ordered pairs are going to be based on your x and y values. So you're going to take those theta values and plug them in for x and y. Now, when you do that, you're going to get out different ordered pairs than what we had before on the other graph, because our circle radius was different. And our equations are going to give us different ordered pairs. So at 0, 0, we have a minimum. I plugged in pi both into x and y equations, and I got 3 pi and 6 as a maximum, and 6 pi and 0 as a minimum. So we have all these critical points, but because our graph went all the way up to 6, we're not going to have, we're going to have 3 pi comma 6 for that maximum point. Okay, so going by the cyclical nature, we're going to conclude that we have minimum points at 0, 6 pi, 12 pi, 18 pi, and so on. And we're going to have maximum points at 3 pi, 9 pi, 15 pi, or 3 times 2n plus 1 pi. So to get the relative, just think about it as 3 times the length that we had before. Okay, so in general, for any cycloid, you can think about the maximum, minimum sharp point. The minimum turning points, which are the sharp turns at the circumference of the circle. So it's 2n pi times a, and the maximum points are at a times 2n plus 1 pi, or halfway between the sharp turns. Okay, thank you for tuning in to Demystifying Math.